Alright guys, so the next thing I need to talk to you about is horn clauses and definitive clauses. And so this last little subsection here will finish up section 7.6. So as it turns out, with many of the situations that you deal with, you don't necessarily need to use everything that resolution can do for you. You don't need to use the full power of it, right? So there are times when you have knowledge bases that have a certain set of restrictions on the sentences that they can have, right? So if they have that, then they can use a more restricted and thus more efficient inference algorithm, right? So the algorithm can be scaled down and be required to do less work. Okay, so let's examine some of those potential restrictions, right? So one potential restriction is that the knowledge base be made up of these things called definite clauses, or the definite clause. So what is a definite clause? It's a disjunction of literals, so basically a string of ors where exactly one of them is positive, right? So if you look at this top clause right here, that guy right there is a definite clause. Okay, you can see that there is two negatives, right? The not L11 and the not breeze. Okay, and there's only one positive, and that's the B11. Okay, so that's a definite clause. So beneath that, there's an example of something that's not a definite clause, right? Because there are two positives. So a definite clause, there's one positive, right? It's a disjunction. You could have 10,000 literals in there, but only one of them can be positive. Okay, so another restriction, and that is what's called a horn clause, right? So a horn clause is a bit more general. And this is a clause that is a disjunction of literals, like a definite clause is, but you have at most one of them that is positive, right? So with a horn clause, you can have 0 or more positives, right? So let's say that you have disjunction, 3 literals, all negative. That's a horn clause. Let's say you have a clause, it's a disjunction, 3 literals, 2 of them are negative, 1 of them is positive. That's a horn clause too. So what this means is that all definite clauses are horn clauses, right? But not all horn clauses are definite clauses, right? Because horn clause can have one positive and the rest being negative. That's also a definite clause, right? So all definite clauses are horn clauses. Also, these clauses that have no positives, that are horn clauses, they go by another name too. They're also known as goal clauses, right? So that would be a disjunction where you get 4 literals and they're all negative, right? So not A, or not B, or not C, or not D. Okay, that's a horn clause, and it's also known as a goal clause. Okay, so a lot of terminology to throw at you there. One other little factoid here, that under resolution, horn clauses are closed. Okay, so what that means is if you got 2 horn clauses and they resolve against each other, right? You have some elimination that's going on, some cancellation that's going on, they resolve each other. The resulting clause is itself going to be a horn clause. Okay, so what's the point, right? Well, if you have a knowledge base that has only definite clauses, okay, then that's going to be interesting for a few different reasons, right? We care for a few different reasons. Okay, one is that the definite clauses, they can be rewritten. Okay, they can be written as an implication where you have a conjunction premise, okay, which is an and, right? A couple literals joined together by ands, and they're going to be positive literals, and that implication will have a conclusion that's a single positive literal. Bear with me, this is going to bear fruit. Okay, so an example of a definite clause, not L11 or not breeze or B11, right? There's exactly one positive literal in there. Okay, now we can rewrite that as the implication underneath it. L11 and breeze implies B11. Okay, so what's the benefit? Who cares? It's easier to understand, okay, for one, in this form. So how do we read this, right? How can we read, compare the two, right? On the second line, we can read that as, well, if the agent is in square 1, 1 and there's a breeze, then that means that square 1, 1 is breezy, right? Agent's location is 1, 1 and there's a breeze there, it takes a breeze, therefore that square is a breezy square, right? Compare that to the previous clause. Nobody in location 1, 1, or there's not a breeze there, or it's breezy. What? Right? That's a little bit more complicated, right? If we rewrite it in that implication form, something becomes pretty darn easy for us to be able to see what's going on, what it means. Okay, a couple more quick terms for you here. When you have this definite clause in its implication form, the premise part, which is this part right here, right, the conjunction, that's called the body, right? And the conclusion part, that's this part right here, B11, that's called the head, right? Which is kind of weird, but I guess the conclusion points to the head. So, or excuse me, the body points to the head. Okay, fine. Or maybe the body supports the head. Maybe that's a way to think about it. Okay. So if you have a sentence, another little factoid here, that has just a single positive literal in it, so A, right, or B, or C, or alpha, or beta, right? Just either one of those things on its own, any one of those on its own. You have just a sentence, and the sentence contains, a single positive literal, A, okay? Then that's called a fact. And you can write a fact in the implication form, so you can see right here, I have it on the slide, where true implies L11, right? So, okay, fine, that's the implication form, but if true is always true, right, then we can go ahead and we can just dump that part. We can dump the body of it and just go with the head. Okay, so it's just simpler to write the L11 by itself. Now, file that away, because when we start dealing with expert systems, we're going to be talking about facts and rules, and in Prolog, it's basically built around, that logic inference engine is built around, facts and rules. Okay, now the next interesting thing that's part of the payoff is that we can do inference using horn clauses, and when you do inference using horn clauses, you're performing what's known as either forward chaining or backward chaining. Okay, so inference that revolves around horn clauses are going to be done using algorithms that are performing forward chaining or backwards chaining. Okay, and the algorithms that use horn clauses can make the inference steps really easy for humans to follow. Okay, that's one of their main benefits. And these types of algorithms, forward chaining and backwards chaining algorithms, they're the basis for logic programming, which if you go on and take other classes or classes based in logic programming, you're going to get a lot more exposure to this, and we'll play with it a little bit more, or the text discusses it a little bit more in chapter 9. Okay, so one other fact, right? One other payoff, one other reason why these restrictions are interesting, is that algorithms that decide entailment, that are built or that are based on or using or working with knowledge bases that have this restriction that they have horn clauses, okay, deciding entailment using horn clauses, those algorithms that use horn clauses to decide it, they can figure out if a knowledge base entails a sentence in linear time, which is actually pretty good, much more efficient. Okay, so on this slide I just have figure 7.14 for you from the textbook, which you can take a look at, on your own or in the slides themselves or whatever, but in the video I'll just throw it up here. And this is just the grammar for conjunctive normal form, horn clauses, definite clauses, all in one place, so you can see, compare these things together, compare, contrast, just kind of see them all in one place. Okay, so going to talk about this forward chaining algorithm, and this is the pseudocode for it. And all I'm going to do is give you a high-level overview of how this thing works, and I'm going to leave it up to you to kind of trace through it. For the first 6 chapters, I walked you through the pseudocode line by line, but I need to speed this up, so I won't go through this one line by line. I'll just give you a high-level overview and leave it up to you to trace through it. You should be able to do that by now. Okay, so what this algorithm does, okay, is it's going to start off with a known set of facts, right? So you've got a bunch of positive literals, okay, or the facts that are in the knowledge base, and what it's trying to do is it's trying to determine if there's a proposition symbol, say Q, which stands for some query, some question you're asking. You're trying to find out if that is going to be entailed by a knowledge base that has a bunch of definite clauses in it. Oops. So let's say that your knowledge base has got some facts, right? Some known facts. You start off with those, okay? And your knowledge base has an implication in it, right? So, for example, L11 and breeze implies B11. Okay, so if L11 and breeze are known, if those literals are true, if they were in the knowledge base, okay, then what that means is that you can add, you're safe to go ahead and add the conclusion B11 into the knowledge base as its own separate fact. Okay, so L11 might be a fact that's already in the knowledge base, breeze, a fact that's already in the knowledge base. You have this implication, right? L11 and breeze imply B11. If L11 and breeze are both true, and you know that those things exist, then you can go ahead and add B1. You can add that head to your knowledge base. So the knowledge base grows. Okay. Now you can repeat that process, okay, over and over again until that proposition symbol, that thing you were trying to see if the knowledge base entails, you can keep going until it gets added through this process, or until you run out of inferences. Okay, so I'll give you another example here in just a second. I'll give you a graph and I'll walk through it. But the big thing to remember about this algorithm and why it's such a big deal and why forward chaining is so good is because it runs in linear time. Okay, so let's take a look at an example here, right? So in this figure 7.16a, we got ourselves a set of horn clauses. Okay, so that's a knowledge base, nothing but horn clauses, which means it's nothing but definite clauses. So this algorithm can be run using this knowledge base. Okay, so we've got a couple of facts, and that's A and B. Okay, and we have a bunch of implications, okay, in our knowledge base. Now, on the right hand side here, figure 7.16b, what we have is what's called an and/or graph. Okay, and the way you look at this thing is you can see that you got all your literals, the Q, the P, the M, the L, the B, and the A, and all of the different links, right? So from B to L, for example, those things, whenever you have a couple of links that are joined by arcs, as you do with the link, you know, in between A and B here, like this guy right here, okay? What that does is that represents a conjunction, right? A conjunction. So A and B, okay? So what that means is that each of these links right here would have to be proved, okay, in order for you to be able to proceed, okay, in order for the algorithm to continue propagating, okay? Now, if there's no arc, what you have is a disjunction, okay, and so you can prove any of the links, okay, and these links are representing essentially, you know, well, I'll show you, okay. Okay, so that forward chaining algorithm, let me use a different colored pen here so it's easier for you to see, right? So you start off with known leaves or known facts, okay, and that's your A and your B, okay, that's how it starts off. And so the inference, the chain of inferences, okay, the implications here, they're going to propagate up the graph as far as possible. Because remember, we're trying to see if the knowledge base entails Q. Right? That was the goal. So whenever you have a conjugation, okay, then the algorithm has to wait to propagate. Right? It has to figure out or wait for all the conjuncts to be known before proceeding. Okay, so you know, the A has to be known, the B has to be known, or you know, if you're looking at L and M, then the L has to be known, the M has to be known. Those things have to be proven. Okay, so textbook says try it, see if it works, right? Well, if you start off with A and B and both of those are true, what does that get you? Right? It gets you A and B, which implies L. Well, A and B implies L. Okay, so you've propagated this far. Now, if you want to continue getting up to Q, you have to, you know, try to keep moving up north, right? So B and L, right? B and L can imply M, so B and L can imply M. That gets us a little bit further, okay? Now, what about M and L, right? Well, there's M and there's L. That's that implication right there. Well, that gets you to your P, right? And then P implies Q. That gets you to your Q, right? So that, what that illustrates is the series of implications that you have to do, okay, to get from your starting point, which is A is known and B is known, right? That shows you how the proof progresses, okay? A and B implies L, right? Or, you know, A and B implies L, so we can get to L, right? L and B implies M, so that can get us to our M, right? So we've proved that. So M and L implies our P, so we can get to there, okay? And then P implies Q, so we can get to Q. So that's an example of forward chaining. We're starting with known facts, we're applying a series of implications to get us to our query, to get us to our symbol. So based off of that, we can say that this knowledge base entails Q. Okay, that's how it propagates, that's how it proceeds. All right, so a couple notes about forward chaining. It's both sound and complete, okay? And forward chaining is an example of reasoning that is data driven, okay, or data-driven reasoning. So what does that mean? It means that the reasoning, that chain of implications, that chain of inferences, that is going to begin with known data, right? You start with known facts, and then you continuously apply implications to try to get you to that sentence, that literal that you're trying to see if the knowledge base entails. Okay, so when would you use this, right? Well, you can use an algorithm like this when you have an agent that needs to derive conclusions. Okay, it needs to figure something out based off of percepts that it's perceiving, right? Based off of incoming percepts. So in such a agent, a specific query isn't always needed, right? You don't always need something that's specific, like I need to know if this knowledge base entails, this fact. Okay, you can just take the percepts and then let the algorithm run from there. So let me give you an example. If you have Wumpus World, that agent could do a tell, right? And it would feed its percepts into the knowledge base, okay? And in such a knowledge base, you could then use an incremental chaining algorithm to add new facts to what was referred to as that agenda in the algorithm, which could then begin new inferences, okay, or that could get you some new inferences. So as the agent's perceiving things, you're adding those percepts to your knowledge base, and so as you add a new percept, well, then you can start a new inference, right? So percept inference, percept inference, percept inference, percept inference, and then you can be adding facts that are the result of those inferences. So the knowledge base is growing, bit by bit. And humans do something very similar, okay? So let me give you an example. So, you're at home on TV, they're like, the governor has issued a shelter-in-place warning. COVID-19, very dangerous, you must stay home. Okay, so you can infer from that, you perceived shelter-in-place order. So you can infer, I probably can't go to the movies now. Okay, and so that is a new fact, right? That's been added to your knowledge base. Now, it's not going to occur to you that 3 people at a nursing home now have COVID-19 or now have died. Okay, you had a percept, you perceived I probably can't go to the movies, and that's as far as you went. There wasn't some specific query that said, was there 3 people in the nursing home as a result of, this shelter-in-place order? No, I mean, you forward chain just enough as a human being to keep from being overwhelmed, and it's an incremental process. You only do that enough to make some kind of decision right now, right? So an agent can work in a similar way. All right, so a backward chaining algorithm is going to work backwards from the query, okay? So if some query in Q, right, and Q being the symbol that you're trying to see if the knowledge base entails, if it's known to be true, well then done, right? If it's already in the knowledge base and it's true, okay, fine, done. Otherwise, what? Right? Search the knowledge base for implications that have a conclusion of Q, okay? That have a conclusion of Q. Now, if all of the premises of the conclusion are proved to be true, then Q itself is true, right? So you start off with the thing that is meant to be proved, and then you search your knowledge base for implications where their conclusion matches Q. And then you examine the premise part of the implication. You say, well, are all those true? Yeah, okay, cool. Then we're done. Okay. But if all of the parts of the premise aren't known to be true at that instance of time, well, you can just recursively apply this backward chaining until either you run out of premises to examine, or you come across an implication where all of the premises are true. So in that graph that I showed you in the example a second ago, you start with Q and you move backwards until you hit A and B. So a couple of more factoids here for you. It's a lot like the and/or graph search, the algorithm for this. I mean, if you go back to the earlier chapter and examine it, you'll see that there is kind of flows in a similar way. And this is known as a form of goal-directed reasoning, okay? Whereas the forward chaining algorithm is referred to as data-driven. Okay, this is goal-driven because the reasoning begins with the goal rather than with some pre-existing facts. Okay, so this is useful when you want to answer questions like, where's my car? What do I do now? Okay, and a benefit of the algorithm here is that the algorithms themselves, when they're efficient, they can run in linear time, but often they can be much faster than that because you only have to examine relevant facts. You don't have to look through everything, right? So you're actually, this algorithms that use backwards chaining actually use a subset of the facts that are in the knowledge base. You don't have to look at everything because you start off with the goal, you find a matching implication or an implication that has a matching conclusion, and if the premise are both true, well, done, over. Who cares about everything else in the knowledge base, right? So oftentimes these algorithms can run much faster than linear time. Okay, so the next video we'll finish up chapter 7. It's probably the longest chapter in the entire, that we're going to cover. And so you saw that in the links of the videos. There's a lot of stuff here. Best thing I can say to you, the biggest advice I can give to you is, go through the videos, go through the slides, make sure that you understand what's going on. Do a couple proofs on your own. Understand how the propositional logic works at its most base. Understand what equivalencies are. Understand what a definite clause is, what a conjunction is, what a disjunction is. And if you need more deeper understanding, hop in the textbook, read through the relevant section, stop by my online office hours, shoot me an email for any clarification you need. This is a chapter where you really have to engage with the material to understand what they're talking about, especially if you haven't taken a lot of math classes up to this point. It can be tough to wrap your head around. I know it's tough for me to explain it to you, and so I know it's got to be even tougher for you to listen to me try to explain it to you, okay? So if there's any chapter where you're going to be reading the textbook and really digging into it, this is the chapter to do it. And so you might be thinking, what the hell does any of this have to do with computer science? What does this have to do with programming? I want to program, I want to write a program. Because this is the basis for logic programming and logic-based agents and how they make decisions. You have to understand how the logic works at a basic level so that way you can program a logic-based agent to behave in a logical way, okay? And inference engines are built, are programmed, are written based off of what we've just covered. This is how they work. This is at their core of how they're built, okay? And so if you're going to understand how a logic agent is going to work, you have to understand how these inference engines work in terms of, what's the logic that they're built upon, okay? And so the last major PP that we're going to have, programming project, you're going to build an expert system that's going to be based off of an inference engine, and the inference engine you'll use is going to be pre-written for you, and it's going to be Prolog, okay? And so as we move forward in the next chapter, a couple of chapters, we're going to start using language that once you start digging into the Prolog tutorials, you look at the resources online, the logic is going to be the same, or excuse me, the language is going to be the same. We're going to talk about rules, we're going to talk about facts, we're going to talk about forward chaining, we're going to talk about backward chaining, right? And you're going to see that in tutorials they're talking about this, and expert systems are talking using this exact same language, because Prolog is a language that was designed to support programming within this context. Okay. All right, we'll see you in the next video. One more to go for chapter 7.